Okay, so what I want to do today, I'm going to have some time to take any questions over the homework. And then I'm going to introduce you, and you may have seen that I sent you a message about this on Wednesday. But we're going to do an egg drop lab, which you may have done at some point in your school career before. But the idea is I want to introduce it today, because although I will see you Tuesday, Wednesday is an e-learning day. E-learning time maybe is going to build your egg device. And then on Friday, next Friday, when we see you, we're going to drop it. So we're going to talk about that. And we're going to talk about why we're doing it in a unit on momentum. And then we're going to introduce the idea of elastic and inelastic collision. I think I actually want to go a little bit out of order here. Instead of starting, I'm going to take questions on the homework. But I'm going to do that second because I want to do this question first. And for those of you who have maybe gotten through the second section of the homework, you may know why I'm asking this question. But I want to think about, okay, let me back up for a second. What is an impulse? Yeah, the impulse causes a change in momentum. So we define the momentum as the force acting on an object, the average force acting on an object times the time that it's acting on the object, right? And we say that impulse causes change in momentum, right? There's one problem, I think it's like the last problem that you have in the first two sections. It has something like this. I just want to take a look at it. Think about this part. Because just like force is a vector, it turns out impulse is a vector as well. And I want you to see if you can think about what is the impulse in this case. Which direction would the impulse have to point in this case? So tell your partner what you think. Which way does the impulse point in this case where we got a ball bouncing off the wall like this? Anybody want to try? Yes, tell me why, Greg. Why is it only the left? Yeah. That's pretty much the case here, right? So so if you think about what's happening here, right? What's really happening is this ball has a momentum vector that has an x and a y component, right? Which we call px and py. And then this one has a momentum vector that has py and px. The y point is not going to change, right? As long as these angles are the same, this component is the same. This component went from positive to negative, right? So the impulse vector would have to point directly to the left. The reason I want to show you this is there's going to be a problem if you haven't gotten to it on your homework, right? Where it's asking you to calculate this. If, let's say that I knew what that was. So let's say that I knew what this momentum was, and I said that that momentum was the same, right? So let's say I knew these two momentums. How could I calculate that? Uh-huh. Right. So what I could do is I can do some SOHCAHTOA stuff. And the nice thing is that this is a 45, 45, 90 right triangle. If you find one leg, you know both legs, right? But I find the two components, and we know that J is delta P. So that means two things. It means that Jx is equal to delta Px, and that Jy is equal to delta Py. We just discussed how the y component doesn't change. So Jy is 0. So the x component should be whatever Px is, P prime x minus Px, right? And the only difference between P prime and P will be the direction. So you any questions about that? Let's just say, for example, let's say that you did the math and you found that this was, I don't know, I'm just going to make this up. I'm just going to say that this is 8 kilograms meter per second. What would J be? You want to see the pattern? Let's think about this. What's P prime x? If Px is 8, P prime x is -8, right? So Jx would be -8 minus 8. It would be -16. Right? If you get a problem like this on your homework, that's how I would do that, right? It's going to be if you're just going from a positive x component to a negative x component, then your impulse is whatever twice that component. All right. Just to round out this conversation real quick, which direction would the impulse be in this case? This is not a problem. It's just a good one to think about, right? So let's say now we have a ball of putty, and the ball of putty just sticks to the wall. Now, which way does the impulse point? How do you think? All right, you don't want to try it. But no. Kind of going up like. You okay with that? Because in this case, right, both components would be going from whatever they were to 0. Pardon me. So it makes sense. Like if something's running, I want to stop it. I'll put force in that. Sorry. Any questions? All right. What other questions on homework? Go ahead. 9. Atomic nucleus initially moving at 320 emits an alpha particle in the direction of velocity, and the remaining nucleus slows down to 280. If the alpha particle has a mass of 4u. Now, what is a u in terms of mass? Well, I'm going to say in the end it doesn't matter. We're going to look at how the units are going to cancel out, right? And the original nucleus has a mass of 222u. What is speed does the alpha particle have when it's emitted? All right, now I like this problem because it kind of shows the connection between physics and chemistry a little bit. Although if you haven't had chemistry, you may need some help like getting this set up. If you have had chemistry, you'd better remember what an alpha particle is. No. In nuclear chemistry, an alpha particle is just it's helium. It's helium-4, 2 protons, 2 neutrons. And the idea here is you've got a bunch, like you've got so the original nucleus has a mass of 222 U, and it's traveling at, let's see here, 320. If it has a mass, so if it emits, let's see here, let's see. So if it emits an alpha particle, right, the idea is that an alpha particle is going to be 2 protons and 2 neutrons, so it's going to have a mass of 4U, right? So it's going to send something off this way at some, well, let me think about this. Which way does it go? Oh, sorry, alpha particle is emitted in the direction of the velocity. So the alpha particle with an amount of 4U is emitted in the same direction, but we don't know how fast. And now this thing is only going 280 meters per second. Now here's the key. What's the mass of that thing? What? Yeah, 218. Right. This is the key to this, right? Is if the alpha particle breaks off, right, it's not on there anymore. Okay. So if I think about this as conservation of momentum, we have the momentum of the whole nucleus, right? So I'll just call that the momentum of nucleus is going to be equal to the P prime of the second nucleus. So maybe I'll just call it P prime of the nucleus plus P prime of the alpha particle. So I got mass nucleus times velocity of nucleus equals mass of the nucleus prime times velocity of the nucleus prime plus mass of alpha plus velocity of alpha prime. I just called this mass prime because of the mass changed, right? Now, I don't have to like convert everything to kilograms, because since every mass is going to be in the same unit, all the units are going to cancel out, right? So I can just plug in 222 for mass and 320 for velocity, etc. Right? So I think the issue with that problem is mostly kind of understanding like the situation it's trying to explain. But mathematically, it's not going to be very difficult, because now we're in a plug and chug situation, right? And you can, like I said, this is actually, generally speaking, in terms of momentum, generally speaking, you can get by without doing unit conversions as long as all your units are consistent. And it's because all the units are going to cancel out. Is that good, Emma? Anybody else have any further questions on this? Do I need to keep going? Right. What other questions we got? All right. Okay. I would like to just point out going forward, so these 2 sections that I gave you last time, I have them set to be due Monday.
the section 745. Right now, I have it set as Thursday. I think I'm gonna postpone that. But if you look on the syllabus after today, you can do the third section. I'm gonna postpone that, but I gotta look at where I postponed it to. But just for now, you can be working on that. Hopefully, your project sources, right, that we talked about the last time I saw you. Hopefully, those are. Did I do it last time or 2 times? I remember when we did project sources. Was it last time? Two classes ago. Okay. Anyway, so get those done. I'm willing to be flexible on the due date for the project sources, but like the reason I have the due dates as they are is to kind of try and prevent you from getting behind on the project. So again, what I'm asking for is I'm asking for 3 sources cited, and then tell me what information you learned from those 3 sources. Put it in a Word document, and there's a place to upload that. So ideally, you would have that done this evening. I'm going to be honest with you, I'm not looking at it this weekend, so probably Sunday evening makes I won't even notice it. It's not there if it's not there until Sunday evening. And like I said, if you feel like you need more time than that and you want to send me a message, I'm happy to grant extensions on that. I just kind of want to keep track of where everyone's at. So send me a message if you need that. Any questions? Next thing I want to talk to you about is the egg project. I hope this one to be a fun project and not a project that adds too much stress to you. And that's why I said, like, I'm not going to give you any additional work on your e-learning day, because I'm thinking, like, if you block out 45 minutes or so before Friday, between this weekend, between e-learning, right? If you block out 45 minutes, you can build an egg drop project. So I'm going to talk about this. If you'd like, actually, why don't you go ahead and get out your computer, and then you can follow along with me on this. Here's the goal. Next Friday, we are going to take a device that you've built using pretty much whatever materials you want, with a couple exceptions, and I'm going to give you a second, a couple things that I don't allow because it makes it too easy. But you're going to build a device that we can put an egg into and drop off the balcony in the commons, and can prevent the egg from breaking. That's what we're thinking about. You want to know why we're doing this in a momentum unit? Yes, Alyssa. Say it one more time. Sorry. Right. So, let's be clear. It has to do with what impulse and momentum there are. But let's be clear. It's not the impulse per se that breaks it. What is the quantity that breaks it? The force breaks it, but so if we think about that in terms of impulse, right? How can you use impulse to manipulate force? We kind of talked about this last time.
You can make it go for a longer time.
Right. If you do something where you're increasing the time of collision, right? You can make your impulse come mostly through time, and if your impulse comes mostly through time, you don't need as much force, right? So that's one side of it. The other side of it is, well, how do you increase the time of collision? With a cushion, right? We talked about cushioning as changing the time of collision. Hey there. Thanks. So a cushion would increase the time of collision. The other thing you might be able to do on the egg is, what else could you do with it? You could cushion it. Anything else you could do with it? Yeah. Yeah, you could do a parachute or something that slows down the rate. We could follow that.
if you do that, right, what you're doing is you're decreasing the impulse you need. Right? So that's kind of why we're doing it in this unit. All right, here are the rules for this. So you may have done something like this before. The twist that that you may not have done before is I'm giving you a maximum mass of 200. Your thing cannot be more than 200 grams, right? What that means is you can't stick an egg in a container of peanut butter, right? Too heavy. So if you need in a second, I'll grab some 200 gram weights so that you can like get in your mind what 200 grams is. But that's sort of the upper limit on how heavy your device can be. I'll give you the egg. So the other thing that you may have done, if you've ever done this before, maybe you've like soaked an egg in vinegar, or someone told me, I've never heard of this before, but someone told me about like putting the egg in a sock and swinging it around and like, I guess, scrambling it or something so that it was stronger. Someone told me that works. I never heard of it before, but that happened. One of my classes told me that worked. Sometimes you like hard boil the egg or whatever. You can't do that. I'm going to give you the egg. Also, bubble wrap is too easy. You're not allowed to use bubble wrap. Your entire device must not be taller than 75 centimeters. What does that mean? That means that you can't take your egg onto a piece of string and then lower it. That's why that rule is there. Well, okay. So I'm doing it a little bit differently this year, partially because there was one fun lab first semester that water rockets we never got to. But usually I do it where I only allow you to have 5 sheets of paper and like a meter of masking tape. And one time I had one group like cut the piece of paper into like planks, and I let them do it because I thought it was going to fail, because I thought like the tape wouldn't hold and it would break. But then they burned me on that, so I'm not doing that anymore. And then there's going to be basically. This is going to be a friendly competition, so your grade is not going to be dependent upon, like, whether or not your egg breaks. Well, let me, you can get bonus if you win our little contest. There are bonus points, right? I'm not gonna take points off if things don't work the way that you intend them to work, but I will give you bonus if it goes well. And basically the score that you're going to get is given by this equation. So 10,000 is just a constant to make the numbers, but it's 10,000 divided by the mass, divided by the time, divided by the radius. So that means the lightest device that takes the least amount of time to fall, and there's going to be a target that ends closest to the target is the one that wins. All right, so the target will be right under you. Yeah.
So if it hits the target and bounces?
That's a good question.
Well, is it that the time is not stopped until the device comes to a head?
Yeah, so you're right. So we should make the radius where it stops. Yeah. I hadn't thought about it. Like I said, I haven't done it this way before. Yeah. I'm gonna guess. So I'm 6 foot. So I'm gonna guess like, what is it, 7 or 8 feet to the ceiling. It's probably more like 8 feet to the ceiling, and then you got another 2 or 3 feet for the railing. So I'm gonna guess 11, 12 feet. That seems a little bit low now that I'm thinking about like actually standing there. Because it must be, is it higher out there? I think it's high, yeah, so, because we got this, so I'm gonna say, I don't know. You think it's 20 feet? 20 feet over the edge? I don't know. I've never actually measured it, but that's easy. So, anyway, so you're incentivized to make the lightest object that falls the fastest, right? Which might, you got to think about what you want to do with a parachute, right? You may decide that you don't want a parachute to kind of help you fall faster, or you may decide that like you're going to go for the lightness factor and you're going to allow yourself a little bit more time in the parachute. Like I said, the mass, so I mean, I would encourage you if you want to do this. Like I said, in the past, I've allowed 5 sheets of paper and a meter of duct tape, and you can do, or not duct tape, masking tape, and you can do it with that. That's possible, right? So it is possible to make this thing very light if you want to. So anyway, that's kind of what I'm going to ask you to do for Friday, next Friday, and then we'll do the egg drop, and then I've got a lab right up there that we'll do afterwards. But that's kind of what we're. Any other questions at this point? Yeah.
So you only have a limit on how tall, right?
Yes.
Okay.
Yes.
You're making air difference.
So, and I guess I should indicate what the height is. Like, if you then said, oh, well, this thing's just wide, and then you like, then turned it, that doesn't count. Like, when you like drop it, right, whichever way is vertical, it has to only be 75 centimeters.
So can we wait in one end? So wait on both, and then
Yeah.
the whole thing, it's an end thing.
Yeah, and let me just, in case you want something, because I know you may not have a way to measure this at home. So I was just going to give you some 200-gram weight that you could, so you can get in your mind what that is. So, now, how about this? I'm gonna, at some point in the period when we've got work time, you can come up, I don't want to pass these around, you can come up and then you can wash your hands after you touch them, but if you want to know what 200 grams is, like this will kind of give you an idea of what you need to do, right? Basically, like I said, when I say 200 grams, I'm trying to rule out some of the popular designs that are easy, like the one that comes to mind is the jar of peanut butter. So, what's that? I think it just like, I mean, it's essentially a cushion, but it also just like does not allow the egg to move. All right. Any other questions about that? So like I said, I want you to have fun with this. I want this not to be something that stresses you out, but I do need you to bring something in on Friday, because we are going to do we're going to do an analysis of how it went and why. So it is important that you, like, it's not something that you can blow off, but it's not something that I'm expecting you to spend 5 hours on. It's something that I'm expecting you to spend 45 minutes on, or get really interested in it and spend like maybe a couple hours. But really, if you want to spend 45 minutes, like I said, in the past, we've done it in class with 5 sheets of paper and a meter of tape, and we started at the beginning of the period and been done by the end of the period. So I know that it can be done in not much time, but I wanted to give you an opportunity to try something a little bit more creative, because like I said, we didn't, those of you who had Mr. Haiduku did, but those of you who had me, we did not get to a Potter Rocket Lab this fall, and so I wanted to do something to make up for that. Okay, are we all right on that? Okay. I have, if you don't have your notes out, go ahead and get out your notes, because we got one thing we're going to do with notes today. All right. So today I want to talk about elastic and inelastic collisions. You probably already have a little bit of sense when we say elastic. What are you thinking of? Rubber band, bouncing. Yeah, I guess we have talked about elastic potential energy, right? In terms of collisions, these are going to have two very specific definitions. So, and you really should think about this as a continuum. There are very few things that are totally inelastic. There is, in practice, nothing, but in theory, very few things that are elastic in nature. But you should really think of this as a continuum, like how elastic or how inelastic is it? But an inelastic collision is when objects stick together. So the degree of inelasticity, let me actually define it. It's better if I define elastic collision first. So an elastic collision is a collision in which the kinetic energy is conserved. In other words, there's no non-conservative work, right? So when I think about an elastic collision, I don't know, did I ever show that? I don't think I did the demo with the trains in this class, did I? Did I get out my little toy train set for you guys? I think that I forgot to get it out. I got it out for the later class. So here is an approximately elastic collision would be something like this, right? So during the collision, there's very little kinetic energy lost, right? Not only does the momentum transfer from the one car to the other, but the energy transfers from one car to the other, and there's no energy sort of lost in the aspect of the, or in the collision itself, right? So an inelastic collision, I mean, all real collisions have a degree of inelasticity. So inelasticity is basically non-conservative work that is taking energy out of the system. But if you get something that's a totally inelastic collision, so if it's totally inelastic, the objects stick together. So you've already actually seen, like in the homework, there are totally inelastic collisions. We just didn't call it that, right? So a totally inelastic collision is this, right? Where they stick, well, that was blank. Right, so that's where they stick together. That's sort of the most energy that can be lost. I like to think about where does the energy get lost. I like to think about it in terms of if I get a car accident. Most car accidents are very close to totally inelastic. And think about what work has to happen in a car accident. What work has happened? We need a force across a distance that's non-conservative. What is non-conservative when two cars crash into each Yeah, great.
Well, there is friction. In this case, I'm kind of at this point ignoring, because the friction is going to be not because of the collision. The friction is going to be because of the ground. So we're going to ignore friction in this case. I'm going to say what happens, like, how do you know that you've had a collision, right? You've had a collision because there's been work done to the body of your car, right? The work, there's been a force applied across a distance to your bumper that has crunched it in, right? So the work done to crunch two cars together, right? That ends up being negative non-conservative work. And the most negative non-conservative work you could do in a collision would be a totally inelastic collision. And that's where they stick together, right? When I've got, in this case, the work isn't coming from the crunching of the cars together. In this case, the work is coming from, you hear that, like, you hear the collision, right? So in this case, most of the work is coming out at sound, right? When it clicks together. It's definitely a much louder click when you do it this way than when you do it this way. Now, right? There's still, like, I don't have a perfectly elastic collision, but you can tell that it's not as loud. And right where the energy is going in when I'm talking about magnets is it's going into sound when they stand together. Right? And so again, I wrote this as a continuum because in reality, usually you're somewhere in between these. Now, in terms of physics problems, we usually consider things that are totally inelastic and totally elastic. We do that because they're the most interesting to solve. Because like anything in between, you really just need more information usually to solve it. So we usually learn, you've already really learned how to solve this problem. Today we're going to learn how to solve problems that are over here. Just know that in reality, you're usually somewhere in the middle. And so you could kind of think of this being the lower limit and this being the upper limit of what the collision could do. All right, so I want to spend some time thinking about elastic collisions. So I'm going to do an example elastic collision. And we're just going to do this. So imagine two objects, A and B, that have two different speeds, VA and VB. But I'm going to assume, I didn't really draw that very well, but we're going to assume that this one's going faster. As a matter of fact, this is bothering me the way I drew it, so let me try again. So we're going to say A is going faster than B. And then they collide. And then probably what's going to happen is B is going to be going faster than A. Prime. All right, so imagine, so this is me drawing this out, but if you imagine what does this look like, right? What this looks like is, if you watch my hand, right? One's going faster than the other, and then kind of like this. So they both keep moving, right? But there's definitely a collision where there's a transfer of momentum and energy, right? So the one starts out faster and the other one's going faster. And if it's an elastic collision, we're going to say that I can conserve two things. We're going to say that I can conserve momentum and what else do we say is conserved in an elastic collision? Kinetic energy. So sum of kinetic energies equals sum of kinetic energies prime. So I'm just going to expand these out. So I should have PA plus PB equals PA prime plus PB prime. And I should have KEA plus KEB
equals KEA prime plus KEB prime. We know momentums are, pardon the, we're going to have a lot of, several rows here of calculations. So this is MAVA plus MBVB equals MAVA prime plus MBVB prime. And this is 1/2 MAVA squared plus 1/2 MB equals 1/2 MAVA prime squared plus 1/2 MBVB prime squared. And what I want to do, I want to try and get what I'm going to call an elastic collision condition, right? What I want to do is I want to try and combine these two equations in such a way that I can get a simple equation that's always true for elastic collisions, right? So to do that, what I'm going to do is I'm going to do a little bit of simplifying first. So there's a 1/2 in every term here, so I'm going to cancel out all my 1/2s. And then just because I can, I'm going to put all of my A's on one side and all of my B's on the other, right? So if I subtract this term over here, I'm going to have MAVA minus MAVA prime equals, and then on this side, it's going to be MBVB prime minus MBVB. Right, so what I did was I took this term, and I subtracted it over to here, and I took this term and I subtracted it over to there. I'm going to factor out an NMA over here. All right. Convince yourself that all three of these things mean the same thing. Okay with that? Questions? I want to do the same thing over here, right? I want to get all of the A's on one side and all the B's on the other. So I'm going to have, I think, MAVA squared minus MAVA prime squared equals MBVB prime squared minus MBVB squared. So again, I just subtracted this one over here and I subtracted that one over there. And then I'll go ahead and factor out my MA. We okay? We're almost there. This is almost going to turn into something really pretty, but it's not pretty yet. It's pretty ugly right now. You remember how to factor this thing? VA squared minus VA prime squared. How about this? This is a difference of squares, right? So I can say that this is equal to VA minus VA prime times VA plus VA prime, right? And I can say that this side is VB prime minus VB times VB prime plus VB. And this is where we could do something really cool. Wonder what anyone sees as the cool thing we can do. There's some connection between the two equations we're doing. What if I took this equation and I divided it by that equation? Let's watch what happens. I'm going to write this equation out first. MA VA minus VA prime VA plus VA prime equals MB VB minus VB prime VB, sorry, I got my prime messed up. This is VB prime minus VB. This is VB prime plus VB. And I'm going to take that and I'm going to divide it by this equation. MA VA minus VA prime MB VB prime minus VB. Why is that cool? There's a lot of things that can cancel out now. And then I get a very pretty equation. VA plus VA prime, and I'm just going to flip-flop the way I write this so that it's parallel, equals VB plus VB prime. This is what I'm going to call the elastic collision condition. If a collision is elastic, it must obey that equation, right? That equation has to work if ever it's an elastic collision. You just marvel at that for a second. That is kind of cool that there was that really ugly bit of path that turned into a pretty simple equation. Now, there's a caveat to this equation. This equation only works in one dimension. In two dimensions, and we're not really going to do much with that two-dimensional elastic collision. But there is no nice, neat equation for a two-dimensional elastic collision. But for one-dimensional elastic collisions, right, where they stay going along the same line, you can use this equation. So let's see how it gets used. So all that, right, all that we just did, you're not going to have to do any of that again. We're just going to use the result from now on. This result would be something that I would give you on the test. You don't need to memorize this equation. This is something that I would give you, right? But now what I want to do is I want to try and do something with it. Can I move this paper? Anyone still using this? So here's a problem we're going to try. We're going to try a problem where we got a 0.15 kilogram ball that's going 4 meters per second. And it crashes into a 0.18 kilogram ball at rest. Do I want it to be at rest? I don't want it to be at rest. I want it to be going 1 meter per second. That'll make it into a more interesting problem. So my question is, they're going to collide elastically. And my question is, after the collision, what are my speeds? All right. I want to give you a moment to digest the problem and see if you can, using equations we've got so far, see if you can see where you want to go with this. If I got an idea. Or if you feel like you're stuck, where are you getting stuck? Because there is an interesting, I gave you a new equation, right? Can I use the new equation? What's the problem with it? If I write it in terms of these, right? So I'm going to do 1s and 2s instead of A's and B's, because that's what the problem says. It seems like I know that and that, but it seems like I got 2 unknowns. And I do have 2 unknowns. But usually, and you got to think about algebra, if you've got 2 unknowns, what do you have to solve something if you've got 2 unknowns? You have to have a system of equations, right? Is there anything else that is true in this case? So this is my elastic collision condition. This has to be true. Are there any other equations that have to be true? I'm sorry, I heard something, but I couldn't hear it all. I don't know who was, somebody was saying something, but I couldn't hear it. I'm sorry, the masks are bothering me. I can't hear who's, somebody's saying something. No? We could do kinetic energy conservation, yes. Kinetic energy conservation is a pain. So I'm going to do momentum conservation, yeah. So I can also say this. So I can also say this comes out to be like M1 V1 plus M2 V2 equals M1 V1 prime plus M2 V2 prime. And honestly, the easiest way to deal with this, in my opinion, is to plug in numbers. You can do this with symbols all the way through, but it gets a little unwieldy. So I'm just going to go ahead and plug in everything that I know into these 2 equations. So I got 0.15 times 4 plus 0.18 times 1 equals 0.15 times V1 prime plus 0.18 times V2 prime. And I just, like, you could put units here. I'm just trying to keep things easy. So I'm kind of ignoring units just to kind of keep it under control. And if I plug into this equation, right, I have V1, which is 4 plus V1 prime equals 1 plus V2 prime. That's the system of equations we need to solve. How would I solve it? There's more than one way to do it, but anyone see a good way to do this? What do you think, Emma?
Solve for either V1 or V2 and then that equation and then plug those in to the other.
So you're saying if I subtract 1 from both sides, I'll get this. And then I'm going to plug that into here. That's how I would do it, yes. Now you can do, there's a whole host of things you've learned probably, right? You probably learned about, so this is substitution, right? You probably learned about elimination. Have you learned how to do it with matrices? So if you know how to do it with matrices, you could do it. This is usually going to work. So this is usually how I do it. But any way that you know to solve system of equations, you can do. So I'm going to plug that in for V2 prime. Let's see here. Let me make this side of the equation less of a pain. So I think this side of the equation simplifies to 0.78 equals 0.15 V1 prime plus 0.18 times the quantity of 3 plus V1 prime. So that's that. You got that. Questions there. Now, I want to know both velocities. How am I going to find V2 prime? Now I can go back here. So now I can go 3 plus 0.73 has to equal V2 prime, right? I'm just plugging back into this equation. So I get V2 prime is equal to 3.73 meters per second. So elastic collisions are cool because you can take only initial conditions and solve for final conditions from initial conditions, right? I only told you what it was doing beforehand, and you were able to figure out what it was doing afterwards. You can do that for totally elastic collisions and totally inelastic collisions. A pattern that you may have noticed is that on the homework, unless I had one that was stuck together, you had to know something about what one of the objects was doing afterwards, right? Which is inconvenient, because usually what you're trying to do is you're trying to predict something that's going to happen. If you can't predict it until you know something afterwards, right? It's just it's not as useful. So elastic collisions are useful because I could just take initial conditions and I could get finalist conditions from initial conditions without knowing anything ahead of time. Now, one other cool thing I want to show you with this that will always be true for an elastic collision. So what's the difference between, so how fast does how fast does 1 look like to 2, right? In other words, 2 is going 1 meter per second. So how quickly is 1 gaining speed, gaining distance on it? A rate of 3, right? Does everyone see that? Because this is going 3 meters per second faster than this one. How much faster is 2 going from 1 afterwards? 3 meters per second faster. So another interesting thing about elastic collisions, at least in one dimension, is that the relative speeds do not change after the collision, right? The order changes, right? Because in here, right, 1 was going faster, and at the end, 2 is going faster, but the relative speeds are the same, right? One is going 3 meters per second faster than the other. So that's another handy little check you can do at the end. If that happens at the end, you know you did it correctly. Okay. Like I said, you at this point know how to do the first three sections of the syllabus? Let me get back to this real quick. You know how to do the first three sections of the syllabus? So the new section, this one, and don't panic about the due date. It's not going to be due Thursday, but that's what your syllabus says right now. I got to update that. But you can do these three sections of the syllabus. Don't forget about your project sources and your egg project. Like I said, there's nothing stopping you from getting started, but that's specifically what I'm going to be asking you to do on Wednesday when you have your e-learning day at home. But that's what we've got. Anything else? All right, we've got 20 minutes to work.